So Giacomo got his PhD in Scuola Normale Superiore in Pisa, in Italy, in 2016. And then he was postdoc at the University of Copenhagen, where he got a Marie Curie Fellowship in 2018. After that, he was a postdoc at MIT in the US, and then he became a tenure-track assistant professor in mathematical physics at Scuola Normale Superiore still. So actually, right now, Giacomo is an associate professor in mathematical physics at the University of Bologna. So the title of his contribution of today is the quantum Wasserstein distance of order 1. So please, Giacomo, go on.
Okay, so thanks for the nice introduction, and thanks again for the kind invitation. So here I will present now like a series of recent results from me in collaboration with Dario Trevisan from Pisa, and with the group at MIT, Milad and Seth, and with Camvise, that is now at the university, at the Technical University of Munich. And these results are about a quantum generalization of optimal mass transport, and in particular of the Earth mover's distance or Wasserstein distance of order 1. So. Okay, let me start with introducing what is optimal mass transport in the classical case. So the idea of optimal mass transport is to consider probability distributions on some metric space as distributions of a unit amount of mass, so that the probability will like them. The probability of a given event will be associated to a quantity of mass that stays in that location. And then we consider like two probability distributions. We will call them mu and nu. You see here a picture. Can you see my cursor? Okay. So yes. Let's say we have, so the metric space is the real line, we have this distribution mu, and we have this other distribution nu, and we want to move this initial distribution mu such that this mass takes the shape of this second distribution nu. And we will associate a cost to this moving. And in particular, we will say that moving a unit amount of mass from a point X to a point Y will have a cost that's equal to the distance between X and Y in the metric space. And then for the whole moving of mu onto nu, we will sum these elementary costs over all the little amount of mass that are moved from some location here to some other location there. And of course, there are many possible assignments or where like an initial amount of mass here goes there, that will result in bringing this distribution nu over the distribution nu. Each of these assignments has the name of transport plan and has an associated cost. And we will be interested in finding the minimum among all these costs. And this minimum cost has the name of transport distance between nu and, okay, here there is some, I should have called the distributions mu and nu also in the text. There is this mismatch for the names, but still, we call transport distance or Wasserstein distance over order 1 this minimum cost to transport the first distribution onto the second. And actually, this provides some distance between probability distributions that has the property that if we look at the distance between two Dirac deltas, like for example one here and one there, we exactly recover the distance between the centers of these Dirac deltas on the metric space. So this is a distance between probability distribution that takes into account the distance of the underlying metric space. And a property of this distance that will be fundamental for the quantum generalization that I will propose later is that this distance is actually induced by a norm on the probability, on the vector of the probability vector. So this means that the distance between mu and nu is actually only a function of the difference mu minus nu and not a function of mu and nu separately. And also I have to say that optimal mass transport is like a huge topic in geometric analysis, and has had countless applications in several other fields like probability, but also fields that are not so close to mathematical analysis like information theory and also machine learning. And finally, when we will consider the quantum generalization of this, we will consider the classical setup that is the closest to the quantum setup that we will consider is the case where the underlying metric space is the space of bit strings, and the distance that makes this space into a metric space that we will consider is the Hamming distance. So I recall that the Hamming distance between two bit strings counts the number of different bits between the strings. Okay. So let me move to the quantum version. So first, I will introduce what are the quantum systems that we will consider on which we will define this quantum version of the optimal mass transport distance. And these systems are made of a bunch of what are called qudits. So what is a qudit? A qudit is a quantum system that has a d-dimensional associated Hilbert space. And when we consider a composite quantum system made by several, for example, here several qudits, the Hilbert space of the joint system is the tensor product of the Hilbert spaces of the single systems of the components. So for example, here we will consider n qudits. CD is the qudit, the Hilbert space associated to each qudit, and then the total Hilbert space will be CD tensor n. What does this mean? So what is an orthonormal basis for this? Let us choose an orthonormal, like the canonical basis for CD, and I will label in this way the vectors of this canonical basis with an integer that goes from 1 to d. Then an orthonormal basis of CD tensor n will just be a string of n symbols, each of which, like each symbol will be able to take values from 1 up to d. And then these base vectors of the canonical basis are just labeled by strings of symbols. And here we can directly see the connection with bit strings. So bit strings were the classical elements of the metric space. Here, these classical elements of the metric space are promoted to basis elements of some Hilbert space. So what will be, I still have to say what is a quantum state of this system. And a quantum state of this system of n qudits is simply a positive semi-definite operator, linear operator on acting on this Hilbert space with trace 1. So the positivity is the counterpart of the positivity of a probability distribution in the classical setting, and the trace equal to 1 is the counterpart of the fact that in the classical setting, when you sum the probability of all the elementary events, you have to get 1. And then I will also need the notion of observable in the quantum setting. So in the in the classical setting, an observable is just a function, a usually real valued function on the metric space, while here the quantum observable will be an Hermitian matrix on the Hilbert space And the expectation value of this quantum observable, for example, I will denote it with H, on the quantum state rho is simply the trace of rho H. And this is just the counterpart of what you would have classically by having, like, by integrating the function according to the probability distribution of the arguments. So, like, these qudits are the quantum systems on which quantum that can be manipulated by quantum computers. And I will need in the following the notion of a quantum gate. So a quantum gate is a kind of like the quantum counterpart of an elementary logical operation on bits. And here this quantum gate is given by some unitary operator acting on the hyperspace, but this unitary operator, like as elementary logical gates only have few bits as inputs, here, these quantum gates have only a few qudits as inputs, and typically, like, gates have two qudits as inputs. So they only act actually on 2 out of the n qudits. So the most natural distance on from the space of probability distribution, that's like if you have an abstract, like, probability distribution on some abstract measure space, and you do not have an underlying distance on the space, the first distance that you consider is the total variation distance. And the total variation has a quantum counterpart. This quantum counterpart of total variation is called the trace distance. And given the density, like, 2 quantum states, rho and sigma, this trace distance is equal to 1/2 of the trace norm of the difference rho minus sigma, where the trace norm is just, in this case, the sum of the absolute values of the eigenvalues of rho minus sigma. And you can check that if rho and sigma are diagonal in a given basis, then this trace distance actually coincides with the classical total variation distance. Okay, so I have introduced what qudits are, what are these quantum systems that we will consider.
Sorry for interruption. I want just the field in the Hilbert space is R?
No, it's real? Complex. Hilbert space is complex.
So what's the dimension of this Hilbert space?
Okay, here in this case, the dimension, you can count how many basis vectors are there, and then it's clearly d to the n. Because here, like, basis vectors are strings of symbols that can take d values, and there are n of those symbols. So you have d to the n possible strings, and so you have an orthonormal eigenbasis with d to the n elements, and that will be the dimension of the Hilbert space.
Okay, thank you.
The important thing is that this dimension grows exponentially with the number of qudits, of course, like as the cardinality of the set of strings grows exponentially with the number of symbols that are there. And in particular, I will always be talking about finite dimension. Okay. So now I will say a few words on why we want optimal transport distance in the quantum setting. And actually, the motivations are quite similar to the motivations to have the transport distance in the classical setting. But first, like, probably there are some more reasons in the quantum setting to want optimal transport distance. Because, like, in the classical setting, like, we start to build this transport distance with the distance in the underlying metric space. So in this case, we have for bit strings, we have the Hamming distance. And we all know that the Hamming distance is ubiquitous with like countless applications in fields like probability, information theory, machine learning, and much more. Like more or less every field that considers bit strings for something will need the Hamming distance for the applications. And the striking fact is that even this step 0 of having a distance between the Dirac deltas is not done in the quantum setting, because the quantum counterpart of a Dirac delta would be a pure state that is a rank 1 projector. And there is, like before our work, there was no counterpart of the Hamming distance for pure states. Like you can define it for the basis states, for the states of the canonical basis, and you can copy the classical Hamming distance, but this was not there in the general case. And like the only distance that was there before people started looking at optimal transport is this total variation distance and distances that are similar to that one. And as in the classical case, total variation does not capture the fact that if you act, like if you have many bits and you act only on a single bit, in some sense, this can be considered as a small change, but of course, in total variation, it can produce a probability distribution with orthogonal support with respect to the original one. And with respect to total variation, every couple of distribution with orthogonal support, like with disjoint support, are considered maximally far, and there's no notion to tell that if you are changing only a single bit, it's a smaller change than changing all the bits. And then what we are looking for is a quantum distance with this property. So first, we would like to recover the Hamming distance for the states of the canonical basis. And we would like this distance to be robust with respect to operations that act only on few qubits. And as a consequence of this, we would like global quantities of the system, like the total energy or the total entropy, to have nice continuity properties with respect to this distance. So let me come to our proposal as definition of optimal transport distance. So actually we started from this idea that touching a single qudit should not produce a large change. So we define two quantum states as neighboring when they coincide after discarding one qubit. And with discarding one qubit, I mean marginalizing that qubit that is considered the marginal state on the remaining n-1 qubits. And then what we want is that we want that any couple of neighboring states must have distance at most 1, because this is what happens for the classical transport distance based on the Hamming distance. And actually, so we want there is this technical assumption that we want this distance to be induced by a norm on the space of the matrices on the Hilbert space, because this is what happens in the classical case. So that every couple of neighboring states must have distance at most 1 means that the norm of their difference must be at most 1. And then this means that the difference between neighboring states must belong to the unit ball of such norm. Then we all know that a norm is completely determined by its unit ball. And then we have a very easy way to define a norm with this property. That is, let's define the unit ball of this norm as the convex envelope of the differences between neighboring states. And in this case, what we will get is the maximum norm that has this property of assigning distance at most 1 to any couple of neighboring states. So we take this as definition of the quantum, this definition of a quantum optimal mass transport norm, and we will call it Wasserstein norm of order 1 or W1 norm. And actually, a nice thing about this norm is that it's it can be shown that this norm can be computed with some semi-definite program. So even if from the definition it would seem maybe a bit cumbersome to compute, actually can be shown that there is some semi-definite program that computes this norm. So you can write down an efficient algorithm to find this distance between couples of states. Okay, so we have a definition, and it's rather simple one. Then let's look at the properties of this distance that we have just defined. So the first thing that you will surely have noticed is that in the classical setting, the Wasserstein distance of order 1 is not defined in that way. So you may ask, okay, but if I use this definition in the classical setting, what do I get? And the answer is that you get the same thing. So in the case of bit strings and with the endowed with the Hamming distance, this definition that I have just given is an equivalent way of defining the quantum Wasserstein distance of order 1. And in particular, if you consider this quantum version of the Wasserstein distance of order 1, if you consider states that are diagonal in the canonical basis, you will exactly get back the classical Wasserstein distance of order 1. So this is a proper quantum generalization of that distance. And in particular, as I were asking between the required properties, in the case of the states of the canonical basis, this distance exactly recovers the classical Hamming distance. So the distance between the projectors on this canonical basis vector will just count the number of different symbols in the string that's associated to the vector. Then this distance has some nice properties that are in common with the classical case. The first is extensivity. And this means that if we consider a bipartite system AB, so this means that we have like our qudits are split in two subsets that we will call A and B. Then the distance between the global states is larger than the sum of the distances between the marginal on the subsystem A and the marginal on the subsystem B. And then we want to relate this distance with the trace distance that I have defined a few slides ago. And this distance is always contained between the trace distance and the number of qudits times the trace distance. And this relation will be identical for the classical transport distance and the total variation distance in place of the trace distance. Then I was talking about local operations. So let's consider two quantum states that rather than differing on a single qudit, they differ on a small number of qudits. So they differ in some region A. So A is some subset of all the qudits. And this means that when we marginalize over, like when we discard these qudits, the state will coincide. So the marginal on the complementary qudits will be the same. Then what happens is that the transport distance between those two states can be at most twice the size of the region, that is the number of qudits in the region. And this factor of 2 actually is a quantum effect in the sense that it will not be there in the classical case. Like it is not there in the classical case.
Sorry for interrupting, second time. I think I have a difficult time to understand notations. When you write the indexes, row A, B, can you comment on the notation you are using in?
This row AB is a quantum state defined on the global Hilbert space that has the qudits in A and the qudits in B. So this Hilbert space will be the tensor product of Hilbert space associated to A times the Hilbert space associated to B. And then this row A and row B are the marginals of row on the qudits only of A or of B. You can, maybe it's easier to think about this in the classical setting as this joint probability distribution for two sets of random variables. And these are the marginals on the two sets of random variables.
Okay.
And this, this will be a partial trace that is the counterpart of what you do classically. Like when you want to get a marginal classically, you integrate or sum over the variables that you are discarding. And this is exactly the same thing. Like if you have a probability distribution on two variables x and y, if you want to get the marginal on x, you sum over the values of y.
Yeah, I got some ideas. Thank you.
And this is exactly the same. Okay. So, and another nice property of this distance is that it's robust with respect to the application of a quantum circuit with few layers. So here is depicted what I mean with quantum circuit. On the right, we have the inputs qudits, and these rectangles are gates that are unitary operation that acts. So this horizontal line represents qudits, and the time goes from right to left. These rectangles represent gates that act on the qudits that they touch. And you can define this notion of light cone of a qudit in the inputs as the number of qudits that can be influenced by that qudit. You can do exactly the same thing if you replace qudits with bits and gate, like these quantum gates with logical Boolean operations. And the result is that the application of this circuit can expand this distance by at most twice the size of the light cones of these input qudits. So if a qudit in the input can influence only few qudits in the output, then this circuit cannot expand by much this transport distance. And again, this will be exactly the same in the classical case for logical operations, except that this factor of 2 would not be here. Okay, then let me continue. So another important kind of distance measure between probability distribution is the relative entropy or Kullback-Leibler divergence. Okay, it's not really a distance because it's not symmetric and it does not satisfy the triangle inequality, but it's a measure of closeness. So in some sense, it can be considered a distance. And this relative entropy has a quantum counterpart that's called, with no surprise, quantum relative entropy, and is given by this expression here. The relative entropy between rho and omega is the expectation value on the state rho of logarithm of rho minus logarithm of omega. And if the states are diagonal in a given basis, this exactly coincides with the classical definition. Now there is a fundamental inequality that relates trace distance with relative entropy. and it's called the Pinsker's inequality, and more or less tells that the trace distance is upper bounded by the square root of the relative entropy. And this inequality is the same in the classical setting with the total variation in place of the trace distance. And like a nice property, like trace distance is upper bounded by 1. So if this right-hand side is larger than 1, this inequality becomes empty. So we can ask whether we can get any improvement over this inequality in the quantum setting by replacing the trace distance with our optimal transport distance. And the answer is yes, but only under some hypothesis. And the simplest of these hypotheses is that the state omega is a product state, and this means that the qubits, the n qubits, are completely uncorrelated. And in this case, what we get is that 1 over n times this transport distance of order 1 is upper bounded by the square root of the relative entropy divided by n. Now, the nice thing about this inequality is that it behaves in a nice way with respect to tensor product, because here, if, like, for example, rho is made by many, like, is a product state with all the copies that are IID, and omega is the same, it can be proved that this left-hand side does not depend on n, and also the right-hand side does not depend on n, because exactly this W1 distance and the relative entropy are both additive quantities with respect to the tensor product. And then, like this result is stable upon taking many independent copies of the states. And for this reason, it's nicer than the original Pinsker that does not behave in a nice way if we take many IID copies of the state, because, like, on the right-hand side, we will have, like, this relative entropy is additive, but the trace distance cannot be additive because it's upper bounded by 1. Okay. Let me continue. So in the classical setting, when you have a function defined on a metric space, you can define the Lipschitz constant of the function. Okay, let's say here, for simplicity, that the metric space is finite. So the Lipschitz constant of a function will be defined as the maximum of the variation of the function divided by the distance between the points. And now the interesting property is that we can propose a quantum generalization of this Lipschitz constant in the case of qudits. And this generalization can be expressed in the following way. So for each, like, we have some, like, in place of the function, we have an observable H that will be some Hermitian matrix on the Hilbert space. And then for every qudit I, we try to subtract from H some observable that does not act on that qudit. And then we want to minimize the operator norm of this difference over all the possible subtracted term. So this is this minimization. And this will, in some sense, quantify how much this observable H depends on that given qudit I. And then if we want a Lipschitz constant, we take the maximum of this quantity over all the qudits. Now, as for the Wasserstein distance, like the classical Lipschitz constant is not defined this way. So you would ask what you get if you apply this definition to the classical setting. And the answer is that you get exactly the same thing. So this is for observables that are diagonal in the canonical basis. That's another way of rephrasing the definition of Lipschitz constant when this distance, where d is the Hamiltonian distance. And in particular, this quantum Lipschitz constant that I have just defined for operators diagonal in the canonical basis will recover exactly the classical Lipschitz constant. Now, what is the relation between this quantum Lipschitz constant and the optimal mass transport distance that I have defined? The relation is that this Lipschitz constant provides a dual formulation of the quantum optimal mass transport distance. That is, the distance between the state rho and the state sigma can also be expressed as the maximum difference in the expectation values on rho and sigma of observables that have Lipschitz constant at most 1. And actually this provides, like I anticipated, that this W1 distance can be computed with a semi-definite program. And this maximization is exactly the dual program of the program that computes the quantum Wasserstein distance. And I also have to say that exactly the same thing is true in the classical case, where, of course, here you would have the difference in expectation values of a function with Lipschitz constant at most 1 on the two probability distributions that are considered. Okay, so a nice property of, like, in the classical setting, the Lipschitz constant controls the smoothness of a function. And a nice property of smooth functions in high dimension is that they are essentially constant, in the sense that the probability distribution of the value of the function when the input comes from some IID distribution is exponentially peaked around its average. So we may want to check whether the same happens in the quantum setting with respect to our new definitions. And actually we found that the answer is yes. So we consider some generic observable H, and for simplicity we will consider that H is traceless, and this actually means that the sum of the eigenvalues is 0, or the average of the eigenvalues is 0, such that the average eigenvalue will be 0. And what we can prove is that the spectrum of H lies in some interval that has a size proportional to square root of the number of qudits n times the Lipschitz constant of H. Or you can phrase it more precisely with this inequality that you see here in the bottom. So this tells you that the fraction of eigenvalues of H that are larger than number of qudits times delta goes down exponentially with the number of qudits. So it's exponential to the minus n times something. And this exponential decrease is, of course, controlled by the Lipschitz constant of the observable. And actually, I have to say that in the classical case, you would have the exactly same inequality. So here we get exactly the same result as in the classical case. Okay, so I was talking about continuity of global quantities with respect to our distance. And a fundamental quantity associated to a quantum state is its von Neumann entropy. That more or less is a quantum counterpart of the Shannon entropy of a probability distribution. So given a state rho, the von Neumann entropy is given by minus trace of rho logarithm of rho, or it's the Shannon entropy associated to the eigenvalues of rho. And roughly it quantifies the uncertainty in the state rho. So it will be 0 when rho is a pure state, rank 1 projector, and it will have maximum value when rho is the uniform distribution, as it happens in the classical case. So we want to look at continuity bounds for this for the entropy. And the nice property of the entropy is that it is additive with respect to tensor product, or the additive, like the entropy of independent random variables is the sum of the entropies. And actually we found, we have been able to prove this continuity bound for the entropy that is stable with respect to taking IID copies of the state, because here on the left-hand side, we have the difference between the entropies of the state divided by the number of qudits. And this is upper bounded by a function of the normalized transport distance plus the normalized transport distance times logarithm of d square minus 1, where this d is the local dimension. And this function is actually the binary, this function H2 is actually the binary entropy function that is defined here. So the fundamental thing about this inequality is that only intensive quantities appear, because both the entropy and the transport distance are extensive quantities. And when you divide an extensive quantity by the number of constituents of your system, you get a density. That is, you get an intensive quantity like the entropy per particle, the energy per particle. So this inequality only involves intensive quantities. And actually, this inequality is almost identical to what you get in the classical case. So in the classical case, you have a continuity bound for the Shannon entropy with respect to the Wasserstein 1 distance. The only difference is that in the classical case, you would not get a d square here, you would only get a d. And this fact that in the quantum setting, you have a factor of 2 appearing that was not there in the classical case, it's a recurrent property of this distance. Actually, I have to say that this inequality is not published in this form in the paper. Like in the paper at that time, we were able to prove like a worse version of this inequality. And like this only came later, and it's still to be published. The proof of this improved version of the continuity bound of von Neumann. Okay. So let me continue. So before I was talking about this improvement of Pinsker that relates this optimal transport distance with the relative entropy. And I told that the inequality can be generalized, like the inequality, the Pinsker can be generalized from the trace distance to the W1 distance under some hypothesis. And then I showed if you remember, I showed you the simplest case of a product state. And what I did with Cambise is to try to generalize this property to more general states. And actually, the first family of states that we considered is like they are the so-called one-dimensional Markovian states. So what is a one-dimensional Markovian state? We have a chain of qudits, as you can see here in this picture. And you say that this chain is like a state of this chain is Markovian if you select one of these qudits. The qudits on the left of the given qudits are independent from the qudits on the right of the given qudit, given the state of the qudit. And you express this condition, like the formal expression of this condition of independence is the vanishing of the conditional mutual information. So the mutual information between what is on the left and what is on the right, conditioned on the given qudit. And actually, the conditional mutual information can be defined in terms of the von Neumann entropy, of the conditional von Neumann entropy. So it will be entropy of the first part plus entropy of the second part minus the global entropy, where all these entropies are conditioned on a given site, and where the conditional and the entropy of X conditioned on Y can be defined as the entropy of the joint system minus the entropy of the system on which we condition. And these two definitions are identical to the corresponding definition in the classical setting. So to express this inequality, we will, so also in the classical setting, people have explored these inequalities. And usually, these inequalities depend on some properties of the conditional probabilities of the joint probability of the considered, of the bits. So we need a kind of quantum counterpart of what is a conditional probability in order to be able to formulate the result. And the quantum counterpart that we will consider is what is called the recovery map. So the recovery, considering one of these Markov states, the recovery map that recovers the state of the qudit I+1 from the qudit I is a quantum counterpart of the stochastic map that's associated to the conditional distribution of the qudit I+1 symbol conditioned on the ith symbol. So there will, in the classical setting, you will have this classical conditional distribution, and you can associate to this conditional distribution a stochastic map. And this stochastic map, you have to remind that has a quantum counterpart, and we will not need the details of how this quantum counterpart is made. Now the result is the following. So this phi will be this stochastic, this recovery map that is the quantum counterpart of the conditional distribution. And the hypothesis that we need is that this quantum counterpart of the stochastic map should contract the trace distance by some factor eta that will of course depend on the state, that is between 0 and 1. So this is the condition that we assume, that this quantum stochastic map contracts the trace distance. And if the state satisfies this hypothesis, then we will have this version of Pinskers inequality. So we have on the left-hand side, as usual, the normalized W1 distance between rho and omega. And on the right-hand side, we will have, as before, like as in the product case, square roots of the normalized relative entropy. And now we have this prefactor appearing here, and this prefactor depends on this contraction coefficient of this map. And of course, this becomes completely void, like if this map is not contracting, so if this eta is 1, this inequality will become completely empty, because the right-hand side will blow up. Okay, so a second setup that we consider is when we have qudits arranged in some hypergraph. So what is an hypergraph? It's like a graph, but the edges, instead of connecting only two qudits, they can connect a larger number of qudits, like 3, 4, or more. And we will call E the set of these edges. And then the idea is that the edges are subsets or mutually interacting qudits. So we say that two qudits interact if there is some edge that directly connects them. And then we will consider what is called a commuting local Hamiltonian. That is some Hamiltonian that expresses the energy of the system that is equal to the sum over all the edges of the hypergraph of terms. So each term is associated to an edge, that is to a subset of the qudits, and acts only on those qudits. So this is why local, because it's the sum of local terms. And then we have a commuting. And commuting here just means that all these terms are matrices, of course, and we impose that all these matrices have to commute. And then we consider as a state omega the so-called Gibbs state of this Hamiltonian. And what is the Gibbs state? In analogy with the Gibbs measure in the classical setting, the Gibbs state is just a state that is proportional to the exponential of minus a constant times the Hamiltonian. And this is a well-defined quantum state of the system. Okay, now we will have a condition phrased in a slightly different way. So before we had a quantum counterpart of the stochastic map associated to the conditional probability. Here we will have a slightly different map that this selects a random qudit I, and then resets its state according to the let's say to the state of all the remaining n-1 qudits. So this would classically be I select a random component and I erase its state and I reinitialize this component in a state drawn from the conditional distribution of that site conditioned on the state of all the other remaining sites. And then, so this will be associated to this operation will be associated to some quantum map that I will call big psi. And we will look at we will assume that this psi contracts the W1 distance, and we will look at the contraction coefficient of the W1 distance with respect to this psi. And we will, the kappa, we will define this kappa associated to this contraction coefficient as you see here. And actually, people look at this kappa also in the classical setting, and in this case, it's called coarse Ricci curvature, because it can be considered as some sort of this counterpart of the Ricci curvature for discrete systems. Now, let's come back to the inequality that we want. Let us assume that each qudit interacts at most with q qudits. So all these terms in the Hamiltonian that we have seen before, each qudit will be coupled with at most other q qudits. Then we have this inequality here. On the left-hand side, the usual normalized W1 distance. On the right-hand side, the usual square root of the normalized relative entropy, and this prefactor that depends on Q and on kappa. So this is a new family of states for which this inequality holds. Now, I want to show you, I showed you 3 versions of this inequality with the relative entropy, and you will be wondering, okay, but why is this inequality so important? What can be used for? Why should I care so much about bounding the W1 distance with the relative entropy? And here is one of the answers. So this inequality can be used to prove the equivalence between the microcanonical and canonical ensembles in quantum statistical mechanics. So in quantum statistical, what is the canonical ensemble? The canonical ensemble in quantum statistical mechanics is the ensemble that associates to a quantum system with some that has some Hamiltonian H at inverse temperature beta, exactly this Gibbs state that we have seen. So this e to the minus beta h normalized by its trace is the state, the quantum state that the canonical ensemble associates to this quantum system with Hamiltonian H at inverse temperature beta. And then the other main ensemble used in actually both quantum and classical statistical mechanics is the microcanonical ensemble. So here, instead of having this exponential of minus beta times the Hamiltonian, we just have a uniform distribution inside some energy shell. And then you will, one of the main issues in statistical mechanics, both classical and quantum, is to find some conditions where these two ensembles are equivalent in the sense that give the same predictions. So actually this is one of the cases where a distance like the W1 distance can turn out to be useful, because of course these canonical and microcanonical states will not be close in trace distance. This will never happen. But they have hope to be close with respect to this W1 distance. And actually, these inequalities that bound the W1 distance with the relative entropy are exactly the way to prove this. So let us assume that we have that our Gibbs state, omega, satisfies these inequalities that imply that the W distance with respect to omega can be upper bounded by some constant that we will assume to be order 1 times square root of the normalized relative entropy. Then it is easy to prove that any quantum state that has approximately the same average energy as our Gibbs state and approximately the same entropy will also be close to the Gibbs state in W distance. And this is because the relative entropy between, if rho has the same energy as the average energy as omega, then this relative entropy is equal to the difference between the entropies. And then this inequality actually becomes this other inequality. And here we see that the normalized W1 distance is upper bounded by the square roots of the normalized difference between the entropies. And then if this normalized difference between the entropies is close, also this W1 distance will be close. And what does this mean in terms of how wide we have to take this shell? This means that if the fraction of eigenvalues that we include in the shell, if we this difference being less than this difference divided by n being small, means that if we include all the eigenvalues up to the threshold energy, this will be satisfied. But this will be satisfied also if we include a small fraction of the eigenvalues. And in particular, this fraction can almost be exponentially small, in the sense that even a fraction of the kind e to the minus epsilon n of the eigenvalues included will just give you a epsilon here. So you can also consider states that are a bit different from the microcanonical ensemble, only take few eigenstates of the energy in the uniform superposition. And as soon as this fraction that you consider decays less than exponentially with the number of components, these results will prove that your state will still be close to the canonical state in the W1 distance. Okay, so now it's time to come to the conclusions. We have defined this new distance on sets of qudits, and we have used, like I showed, this application to prove equivalence between the canonical and microcanonical ensemble. So there are many directions in which we can move, and like this is because the classical Wasserstein 1 distance is employed in countless several applications. So applications I have not talked about, like the first one is in the context of machine learning for the so-called generative adversarial networks that have the goal of producing of learning a quantum state or a probability distribution given samples. And here this distance can be used as a cost function, as it's already being done in the classical setting. This distance can be applied to study the computational capabilities of quantum circuits, because we have shown it is robust with respect to quantum circuits with few layers. Can be used to explore the robustness of quantum algorithms for machine learning that have a quantum state as input. So you can perturb the inputs by a small quantity in this distance and see how much the algorithm is robust with respect to this change. Or this, like SDMing distance plays a key role in the design of classical codes for error correction. We can, like this distance can play a similar role in the design of quantum codes for error correction. Also can be used in the case of quantum rate distortion theory that concerns the transmission of quantum states where some imperfection is allowed in the recovery. And of course, the role of this distance will be to quantify this error in the recovery of the state. And finally, it can be like, well, another possible direction is to extend this distance to the case where we have infinitely many qudits. So in the case where we have some spin system or some infinite lattice. Okay, so that was all. Thanks for the attention. I'm waiting for your questions.
So thank you very much to the speaker for this nice talk. So I invite here people to raise their hands or to just ask for questions. Okay, so maybe I have a question which is actually was like spoiled by the last remarks. So at some point you have shown the Dobrushin uniqueness condition for a finite dimensional system, and so in relation with Gibbs states. So my question was about how one could hope to extend these concentration inequalities in the context, for example, of infinite dimensional systems like infinitely many qudits.
Okay, we have not looked at that yet, but like probably I will try to follow the same route, so in the sense that this in the Markovian case, the conditional distributions depend only on the neighboring, like they depend only on the neighboring sides and do not depend on all the sides. So the fact that there are infinitely many components will not change these conditional distributions, because you can ignore all of them except from a small finite number. So all the assuming that we have a well-defined notion of distance for in the infinite dimensional case, I think that you can probably should be able to go the same routes and find the exact same result. And the main new feature would be extending this definition of distance in the infinite dimensional case, because like here you find the quantities that are normalized by n, and like one possible way of extending this distance to infinitely, like the case with infinitely many components can be, for example, if you have a system with translation invariants, to define this distance at the normalized distance as a limit of normalized distances on finite subsets of the system. Or I would be happy to discuss other proposals in this direction.
So let me see if I got it. So you are thinking about, like, let's say you have a ZD, and you're thinking about boxes in the boxes, something like that.
I'm thinking, like, for example, we have ZD, we have some translation invariant states, and then we define the distance, the normalized transport distance between the two states as the limit of the normalized distance on hypercubes with a finite length of the side.
Okay, thanks. Yeah, thanks. Other questions?
I can have some general remarks, and I'm not sure if I got maybe you have already mentioned some. I will let me start by, when you say classical, do you mean n equal 2? So you say so how we can see classical with respect to n? So it's n because you say that we have classical formulas and.
Okay, in the classical case, you can replace the qubits by classical bits. So n, like n was the number of qubits, and classically it becomes the number of bits. So it's not 2 in general.
Because at some point when you have written the inequality and to compare the distance, the inequality that involves the relative entropy in the first. And you have said that this distance, the Wasserstein distance.
Here, okay. This one here, you say?
Yeah.
Okay.
I was just remarking that the first we don't. Okay. My question comes from the n that is involved in the second inequality, and
yes.
Inside the square roots.
Yes. The second inequality would be exactly identical in the classical setting, with the n in the same position, with the same constants.
Okay. Okay.
And the n in the classical setting is the number of components that will be number of bits, or they can be also symbols that can take more than 2 values. It's not necessary that they are bits.
And what is the relation with between this inequality and the inequality that involves the pre-factor later on?
Okay, because here the omega is a product state. This means that the qudits are not correlated, or in the classical setting, you will say you have n independent random variables, or the bits, like the probability distribution for the n bits are independent. While in the subsequent results, like here, the qudits are no longer independent and the state is no longer product. But okay, the key point of this result is that even if the state is not product, under some condition, a similar inequality still holds. And this is important in the, like, for the final, like for the application, because like here we want to look at the equivalence between canonical and microcanonical ensemble. So the basic result, the one with the product state, we just say, okay, if the qubits are not interacting, so if the Hamiltonian is the sum of terms acting on the single qubits, then the microcanonical ensemble is equivalent to the canonical ensemble. But in general, of course, like most interesting systems do have interactions. And then it's important that this result can be extended also in the case where there are interactions between the subsystems. And then this is why we looked at extending this inequality with the relative entropy also to Gibbs states that are not products, but they contain some kind of interaction between the qubits. Okay, here there is this fact that the Gibbs state is a product state if and only if there are no interactions with the Hamiltonian. This is the same also in the classical setting. Like having a product Gibbs state is the same as not having any interactions in the Hamiltonian. And here, since we want the result to hold even in the case with interactions, at least with some hypotheses, we needed to prove the inequality with the relative entropy in the case of a non-product state, and we managed to do it under suitable condition on this quantum generalization of the conditional probability distribution.
Okay. I have one other maybe in the technical, because at some point, if I understand, you have, when you started to talk about the Lipschitz norm, and you have said that the Wasserstein norm, it can be defined as, can be seen as a dual semi-definite programming.
Yes.
So yeah, so that means that you can see formally you can define the Wasserstein problem as in two different ways, as a minimum of some SDP, then as a maximum of some other dual SDP.
Yes, exactly.
And
this is exactly the same in the classical setting. It's not new of the quantum setting.
Okay.
The only thing is that in the classical setting, it becomes easier, and instead of having a semi-definite program, you just get a linear program.
And the two definitions can be handy in different ways, in different contexts, or you stick to one definition generally in your proofs, or you can use the two approaches, or two.
Depend, actually, if you read the papers that use this distance, like depending on the application, they define it either with the direct program or with the dual, depending on what's easier in that context. In the sense that if you focus more, more or less, if you focus more on the fact that two states that are close in the W distance will have same expectation values for smooth observables, then you would prefer this definition, the dual definition. And this is, for example, if you look at the equivalence of ensembles, you say that you are close to you prove that you are close to the Gibbs state in W distance, and in that sense, you kind of mean that expectation values of smooth observables will be close. And then probably you prefer this perspective. While if for what you need, you prefer the perspective of robustness with respect to local operations that touch only a few qubits, then you may like the other definition. But when you want to prove things, you usually need both. Because usually depends whether if you need upper or lower bounds on it depends whether you need upper or lower bounds to the distance. If you need lower bounds, you use this. If you need upper bounds, you use the other.
That's all for me. Thank you very much for the answer.
So are there any other questions? Okay, so if not, we shall thank again the speaker, and then I will only remind you that we will resume in 2 weeks with the next talk. So we'll hopefully see you there. So thank again, Giacomo, for this talk, and have a nice afternoon, everybody.
Thanks again for the invitation.
Okay. And in 1 month, we will have Thomas Rojoy, and a talk by Thomas Rojoy. So just I want just to do some publicity.
Thank you. Have a nice day.
Have a nice day.
Thank you.
Bye.
Bye. Bye. Thank you.
Thank you. Bye.